Hello and welcome to our video on data structures. Today, we're going to explore some fundamental concepts in data structures. Data structures are essential tools in programming that help us organize, store, and manage data efficiently. They're like different kinds of containers or boxes, each designed to handle specific types of data and operations. For example, imagine you have a collection of books. You could organize them on a shelf, which is like an array, or you could use a library catalog system that sorts books by categories, which is similar to a tree. Understanding different data structures helps us choose the right container for our needs, just like choosing the right box for different items. Let's dive into the basics and get a good understanding of some key data structures. First, let's break down the classification of data structures. Primitive data structures. These are the simplest forms of data structures and include integers, numbers without fractions, like 10 or -3, characters, single symbols or letters, such as A or 7, booleans, values that are either true or false. These are used for making decisions in programming, like checking if a condition is met. These primitive types are the building blocks for creating more complex structures. Non-primitive data structures. These are more complex and include arrays. Think of an array as a row of boxes where each box can hold a piece of data. For instance, you could use an array to store a list of numbers representing the scores of students in a class. Each score is accessed by its position in the array, like scores 0 for the first student's score. Lists. Lists are flexible containers that can grow or shrink. Imagine a to-do list where you can add new tasks or remove completed ones. Unlike arrays, lists can handle changes in size dynamically. Stacks. A stack is like a stack of plates where you add or remove plates from the top only. This principle is called last in, first out, LIFO. It's useful for undo operations in software or managing function calls in programming. Queues. A queue operates on the first in, first out, FIFO, principle, similar to a line at a checkout counter. The first item added to the queue is the first one to be processed. This is useful for managing tasks like print jobs or customer service requests. Now that we have a basic understanding of these categories, let's move on to more complex structures. Let's explore trees and graphs. Trees. Trees are hierarchical structures where each item, called a node, is connected in a parent-child relationship. The top node is the root, and each node can have multiple children. Think of a family tree where each person can have multiple children and each child can have more children. Trees are used to represent hierarchical data like file systems on your computer. Graphs. Graphs consist of nodes, also called vertices, connected by edges. They are great for representing complex relationships. For example, in a social network, each user is a node, and their friendships are the edges connecting them. Graphs can show how different entities are related, such as finding the shortest path between two locations on a map. Let's look at some advanced types of trees and heaps. Splay trees. Splay trees are a type of self-adjusting binary search tree. When you access a node, it gets moved closer to the root. This helps improve access times for frequently used items by keeping them near the top. Red-black trees. Red-black trees are balanced binary search trees where each node is colored red or black. This coloring helps maintain balance, ensuring that operations like insertion and deletion remain efficient. Think of it as a way to keep the tree balanced so that you can quickly find items. Heaps. Heaps are binary trees used to manage priority queues. There are two types, min heaps and max heaps. In a min heap, the smallest element is always at the root, making it easy to access the smallest item. In a max heap, the largest element is at the root. Heaps are useful for tasks like scheduling jobs or managing resources. Now, let's discuss hashing functions and collision resolution. Hashing function. A hashing function maps data to a fixed size value. Think of it like assigning a unique ID to each item so you can quickly find it later. For example, If you have a list of student names and want to find a specific student quickly, you could use a hashing function to assign a unique ID to each name. Sorting algorithms. Bubble sort. This simple algorithm repeatedly steps through the list, comparing adjacent items and swapping them if they're in the wrong order. It's like bubbling the largest unsorted item to the end of the list. Selection sort. This algorithm repeatedly selects the smallest, or largest, item from the unsorted part of the list and moves it to the end of the sorted part. Insertion sort. This algorithm builds the final sorted list one item at a time. It takes each item from the unsorted part and inserts it into the correct position in the sorted part. Merge sort. This algorithm divides the list into halves, recursively sorts each half, and then merges the sorted halves. Quicksort. This algorithm selects a pivot item and partitions the list into items less than the pivot and items greater than the pivot. It then recursively sorts the partitions. It's like dividing the list around a pivot and sorting each partition independently. Topological ordering. This is used for ordering tasks or events based on the dependencies. It's like scheduling tasks where some tasks must be completed before others can start. For example, in a project with multiple stages, you need to complete stage 1 before moving to stage 2. Conclusion. We've covered a broad range of data structures and algorithms today, from basic concepts to more advanced topics. Each data structure and algorithm has its own strengths and uses, and understanding them helps us solve problems more effectively. Thank you for watching. If you found this video helpful, please like and subscribe for more content on data structures and algorithms. See you next time.